All right, section 2 of chapter 14. This is the most important section of the chapter. This is like the guts of it. Um, Solution concentration. So when we have a solution, we like to talk about concentration. There's different ways we can talk about concentration. There's really qualitative descriptions like, oh, it's a weak solution or it's a strong solution. Weak just kind of implies it's very dilute. There's not a lot of stuff in there. Strong, you might think it's okay, it's really concentrated, but those are pretty darn vague and not super useful in a chemistry lab. Getting a little bit better, we have saturated, unsaturated, and supersaturated. I want to go over those, and then I'm going to get to the real ones, the quantitative ones. So let's go over these three qualitative ones. So what do I mean when I say I have a saturated solution? Well, a saturated solution has dissolved all of the solute that it can at that temperature. All right, so how much solute can dissolve? That is temperature dependent, so we'll get to that later on. But imagine you go out to your kitchen, take a spoonful of sugar, put it in a cup of water, stir it around, it's all going to go away. Add another spoon, stir it around, it's going to go away. Keep on going with it, just spoon at a time, spoon at a time. You might notice it gets a little bit harder. You're like trying to stir, and it's like, okay, is it finally gone? You're going to get to a point where it doesn't matter how much you stir, it's not dissolving. And if you add more, the pile of undissolved stuff on the bottom is just bigger, right? At that point, your solution is saturated. It's holding as much solute as it possibly can at that temperature. And what's going on is you've actually hit this point, it's what we call dynamic equilibrium, right? You have so much solute up here that it's actually precipitating. So it's precipitating, going from aqueous back to solid at the same rate that the solid is dissolving into this aqueous stuff. All right, so it's dissolving and it's precipitating at the same rate. You don't see that. All right, this is all going on at the atomic scale, but that's what's going on. All right, so that's what we mean by saturated. It is just, it's loaded up. It's holding as much solute as it possibly can. So what do you think unsaturated is? Dun, da, da. Just means it can dissolve more solute. All right, if it's unsaturated, your solution can dissolve more solute. This is a really vague description though, because does that mean like I can dissolve like one more grain, like one more tiny bit, a milligram more, or can I put in like another 10-pound stuff? You don't know. It's just unsaturated is a really kind of vague thing. It just means it's, well, not saturated. All right, now I'm going to go to my favorite one. There's something called supersaturated. What the heck? Where'd that go? Types of solution. Oh, there we go. Like, it disappeared. I freaked out. My whole slide disappeared. It's good. Phew. All right. Supersaturated solutions. Supersaturated solutions are very weird because they hold more solute in them than is technically possible. It shouldn't be possible. And the way we make these things is we make them at a high temperature and then we lower that temp down. And for certain substances, that solute will stay in solution. All right. It shouldn't be in solution at that temperature because once it cools down, once it gets down to that cooler temperature, like, it shouldn't be holding that much stuff, but it does. That's what we call supersaturated. And come on, thing, geez. They're really unstable. If you like scratch the side of the container, like you could set off crystallization, or a lot of times we can use like a little seed crystal. So if you take a little seed crystal and drop it in, all right, this is probably sodium acetate. Take a little crystal and drop it into the supersaturated solution. It just goes, and all of a sudden you'll see all this solid start forming instantly right before your eyes. Very cool. I will show you some videos of that. If we're in real life, I'd show you that too. All right, let's get to the quantitative stuff. Let's get to some actual things that involve numbers, things that are of more use in a chemistry lab. So we have percent by mass. Click. We also have percent by volume. There's molarity, there's molality, and there's mole fraction. So these 5 are what you guys are going to need to know. So to calculate percent by mass and percent by volume, I'm going to be willing to bet you already know how to do that. You could probably guess. I swear, you could probably just guess what's going to happen with that. So if you have a solution, you're trying to like describe its concentration by a percent, a mass percent, what would you take the mass of? You'd need 2 different masses. What things would you take the masses of? How about the part and the whole? Like, it's part over whole, like any percent is. It's always part over the whole, right? So the part is just your solute. The whole thing is the solution. You take the mass of your solute divided by the mass of the entire solution times 100. That is your percent by mass. Now that you're on board with that, I bet you're able to determine, like you're psychic or something, the percent by volume. Take a wild guess what percent by volume is. Oh my goodness, did you guess it's the volume of the solute divided by the volume of the entire solution times 100? If so, you are correct. So most of these things are going to be solute over solution, right? I'm going to get to the most important one right now, molarity, right? The symbol for molarity is a capital M, all right? So of the 5 different types of solution that we're talking, or ways to describe concentration, this is probably the most important one. This is the most used one for sure. It's moles per liter. So moles of solute divided by liters of solution. So just remember, molarity is moles per liter. Molarity is moles per liter. We will use that a bunch. And you can use that like an equation. So if you do liters times molarity, it gives you moles. If you do moles divided by molarity, it gives you liters. So even though this is the definition of it, it's actually like a working equation. So it's kind of cool. There is one thing about this, that your liters of solution, that can change. That is temperature dependent, right? That's why thermometers work, right? Thermal expansion, right? You have alcohol thermometers or mercury thermometers and those things. And it's because those liquids expand when you add heat to them. Pretty much everything will change, even not a ton, but a little bit. There's, thermal expansion and contraction. All right, so this is temperature dependent. There's another version that we deal with that's not temperature dependent. It's also pretty common. It's called molality, right? It's a lowercase m. So molarity was a capital M. This is a lowercase m. And this is actually the weirdest one of the bunch. It says everything we've talked about so far has been solute over solution, solute over solution, solute over solution. This one's wacky. It's moles of solute over kilogram of solvent. All right, so not the solution, it's just the solvent. So this is the odd one out. All right, it's the only one that's like this. Everything else is part over the whole. So speaking of, let's get to the last one here. Before I get there. So we'll use this in situations where our temperature is changing. So we want to keep track of our concentration, but we don't want it to be temperature dependent. So this does not change with temp. All right, last one here would be the mole fraction. All right, it's usually this big fancy X. All right, fancier than this X. It's kind of like a flourishy fancy X. So the mole fraction of something would be the moles of that something over the total number of moles, all right, in your solution. So all the moles of all the different solutes plus the moles of the solvent. That total number of moles goes in the bottom. All right, this is unitless. All right, these will all be numbers like 0.25, 0.75, or something like that. So that's mole fraction. Gets used a lot, and let's keep on going. There's one more little thing here I need to show you guys, dilution. So when you dilute something, you're lowering the concentration. Imagine make some Kool-Aid. You got some nice, really strong Kool-Aid, and you take a cup of that, but then you go out and add like another 32 ounces of water to your Kool-Aid. It's not as strong anymore. It's been diluted. All right, so when you add solvent, right, to your stock solution, you're dissolving or you're diluting it, right, for aqueous solutions. If it's just the solvent, any solution, but water if it's an aqueous solution. Gosh, losing my mind here. All right, let me get down to the important thing here. This is the equation. So M1V1 equals M2V2. You will sometimes see this as C1V1 equals C2V2. It means the same thing. My initial concentration, my initial volume. Final concentration, final volume. All right, this is a really handy equation. We'll do some examples with it in class, but just write this thing down and get to know it. It's your friend. All right, we'll catch you guys in the next one. See y'all.